Section 4.5, solving exponential and log equations. Quite a long list of problems. Not a lot at the beginning because the web work problems covered those pretty well. Okay, so exponential equations. So the exponential equations, there are lots of different types, but the main idea here is that the variable that you're trying to solve for in the equation is in the exponent spot. So there are lots of different forms for exponential equations, so lots of different strategies, but in most of them, the general idea is to use logs to somehow bring the exponents down out of, or the variables down out of the exponent spot. So I'll show you a few different types. So this is supposed to indicate that we're going to have the same base b on both sides, and that we'll have x's in both of the exponents, some function of x up here and some different function over here. So examples will make it easier. So 5, so base b, 5, is the same on both sides. We have x's in both exponents. Because the base is the same on both sides, the quickest way to solve this is simply to take log base 5 of both sides. 2x, and we're going to be using the cancellation law. Oops, right. So log base 5, a 5 to the is just the thing that's upstairs. So this quickly brings the variables down. This is 2x, and this is x plus 1, and hopefully we are able to solve this. Let's move subtract x from both sides. This is x equals 1. Right, so here's another equation, and it's listed under the form where the equation has the same base on both sides. So this might be a bit of a challenge, but essentially what you're being asked to do is to recognize that this constant on the right-hand side is really 5 raised to some power. So what we're going to do again is just take log base 5 of both sides, and after the cancellation that'll give us 2x is equal to 3, so x is equal to 1.5. I should say that perhaps it's perhaps not essential that you multiply, write 125 as 5 cubed. If you simply took log base 5 of both sides and then computed that the log base 5 of 125 was 3, that would be sort of another way around getting from equation 1 to equation 3. Okay, so here's a second form. Maybe I'll try to close these forms, keep track of our list as we go. This time we've got just a single exponential, and the x's are up in the exponent spot again, but we might have a constant out in front, and there's a constant on the right-hand side. Okay, so here's such an example. How do we solve this equation? Again, the variables upstairs, we want to get them down. We're going to take log base 10 of both sides. That'll, through the cancellation law, oops, be bringing the variable downstairs. So this is log 7 on the right-hand side. Okay. Oops, oh shoot, I had it right. So cancellation law, the left side now becomes just 3x plus 1, and the disconcerting thing, the potentially disconcerting thing, is that the right-hand side is not going to simplify. But it's important, it's critically important to remember that this right-hand side, just some number. So we got to make sure we treat it not with any more respect than any other number deserves. So how do we solve an equation like this? Well, this is a constant. We're just going to subtract 1 off from both sides. Okay, so that's going to, I don't think I want to do a copy. No. That's going to leave 3x equals log of 7 minus 1. Again, this is just some complicated looking number here, but our last step is simply going to be to divide through by 3. We'll need a set of parentheses now. This is log 7 minus 1. Right, just some number on the right-hand side. Okay. Here's another equation, the same form. This time So a single base, x is up in the variable spot, sorry, the variable x in the exponent spot, and a constant on the right-hand side. Okay. So you might be tempted, we want these variables downstairs. If we take the natural log, we'll get this cancellation. But the thing I want to highlight here is that you need to divide through by this 2 first. This is called isolating the exponential. We want it completely isolated. So that constant, we want to get moved, the constant 2, we want to get moved to the other side. Again, we just do that by division. So 8 divided by 2 is 4. And now that the exponential is completely isolated, now's the time to take natural log of both sides. So when we take the natural log of the left-hand side, we get the cancellation, and on the right-hand side, we get natural log of 4. So just as before, we've got to make sure that we treat this just as a simple number, no additional complications other than treating that as a number like any other. So we can't combine this. We don't know what this is as in a simplified form. So we just have to leave that constant that way. And our last step, again, is to just divide through by the 3. So natural log 4 minus 1 in here. Okay. It's looking funny to see these. I'll typeset later. Another example like this, so we're going to divide through by the constant 5. We get 3 to the x, and when we divide through by 5, 20 divided by 5 is 4. And now the cancellation that we might go for here would involve taking log base 3. That would bring the x down really quickly and easily. But our instructions say that we're supposed to express our answer in terms of log base 10, that is common log or natural log. And this is quite common that we make this restriction, again, because a lot of times that's the only buttons we have on the calculator. We don't have a log base 3 button. Okay, so to get our exponent down, we're going to take, and it's completely your choice at this point. Once log base 3 has been forbidden, it's up to you to decide which of the 2 permissible logs to use, either the natural log or the common log. I'll go ahead and use, I guess, common log here. So I'm going to take log base 10 of both sides. And this time it's not the cancellation law that brings the variable x downstairs. This time it's the law of logs, that third law. Okay, so the variable x is now out of the exponent spot, and again, it's just one of these things that takes a little getting used to. These 2 expressions, log of 3 and log of 4, are simply numbers. So we wouldn't have any trouble solving 3x equals 4. We would know, oh yeah, we just divide both sides through. And that's the same attitude we want here. All we have to do is divide through by this constant log of 3, and we've solved for x. Right? And done it in the way that they said. It's expressed in terms of the common log. Okay, so another Hugo problem here. Again, what I'm suggesting is that you pause the video, try to solve this equation. Again, make sure you see that it asks you to express in terms of natural log or common log, and then start the video up again. 3, 2, 1. Okay, so looks like I took common log again, common log of both sides, bring the 2x plus 1 out in front, and then divide both sides by log of 3. Complication, this constant is getting kind of complicated. We have to subtract the 1 over, and there's no simplification. This, as tempting as it might be, this does not simplify to log of 8, so you have to leave it that way. And the last step is to divide through by 2. Okay, so one more type here, and this, it might be hard to parse the difference, but in this form, the bases that we have are different on the two sides. In the first form, we have the same base on both sides. This is what happens, what to do when it happens that the base is different on both sides. Okay, so we have base 10 on one side, base 3 on the other side, and in both exponents there's some x stuff going on. Okay, so what we're going to do is take logs of both sides, and here it's the 10 is one of the bases, and so it's kind of strongly suggests that we take log base 10, or the common log. So I guess I'll write that out in full, because what's going to go on here is potentially different on the two sides. On the left-hand side, you might think to yourself, well, this is just cancellation. Log base 10 and 10 to the 2x. Those give the cancellation. On the right-hand side, log base 10 and 3 to the don't cancel. So on the right-hand side, we need to use the log law to bring that x plus 4 out in front. Okay, and now here things are again confounded, but only slightly because of how strange this constant is. If you can imagine this being just the number 3 instead of log of 3, how would you solve the equation? Well, you'd multiply out 3 times x plus 4. You'd get 3x and 12, you'd collect the x's and so on. So that's what we have to do here as well. On the right-hand side, how many x's do we have? Well, we have log 3 times x. And what's our constant? Well, it's 4 times log 3. It's just, we could write this as x times log 3, but it's so hard to do that. Almost always we put our constants in front of our x's. Okay, so the next step is to move over all of our x's to the left-hand side. So we'll subtract over log 3 of x and leave behind the constant log 4 log 3. And then on the left-hand side, we need to factor. You can think of this as factoring or just sort of doing an overall count. How many x's do we have? Well, we have 2 minus log 3 of the x's on the left-hand side. And on the right-hand side, we still have this constant 4 log 3. And then our last step is simply to divide through by this coefficient on the x. So our x will be 4 log 3 divided by this constant. So again, I know I'm repeating myself here, but a big challenge is just treating these log of a constant as just a normal constant and just dealing with it symbolically. Okay. Right, so here's another one, same form. The bases are different. That's the key part here. Now, the instructions, once again, are saying that we are to use common or natural log. If those instructions hadn't been there, then it would be a good idea probably to use, say, log base 5 or log base 3 to bring our exponents down. But here we've been told that is verboten. So I guess we haven't done natural log, so let's do natural log. And again, it's your choice. So we're going to take natural log of both sides. And it's not cancellation helping us out this time. It's, once again, the exponent law, that we can bring the exponent out in front. Natural log 5, and this is x plus 4 times natural log 3. Right? So on the right-hand side, we have, well, I'm actually going to rearrange this. We've got 2 times natural log 5 x's. Right? The natural log 5 is just a number. So 2 times x times 5 would be 10x. So in the same way, that natural log 5 can go in front. On the right-hand side, it looks like we have natural 3 times x, and we have 4 times natural log 3. Right? we're collecting our x's on the left-hand side. We have 2 natural log 5 of them on the left-hand side, and we're going to be subtracting off natural log 3 of them as we move this term to the left. Right, so that's the total number of x's we'll wind up with on the left-hand side, and the constant left behind on the right-hand side is just 4 natural log 3, and the final step here, once again, is just to divide through by this coefficient on the x. Okay, where are we? We are at 1530, and we'll do our, I guess this is really the last general type, and then there's kind of free-for-alls that don't fit other forms that we'll look at as well. So I guess I haven't given you sort of a symbolic generic form, but I'm just showing you by example here. Quadratic type says that your exponential is going to appear somewhere in the equation to the first power. I don't know if I should put parentheses around this or not. And then somewhere else, this exponential, the thing with the variable upstairs, is going to be squared. So this is quadratic. And what you're going to try to do is factor this like any other quadratic. So we have something squared. So if we're going to try to factor this, it's natural to hope that it might be, e to the x. Well, it's going to be plus or minus something here. We don't know. And then the other term will also have an e to the x in it. Ooh, I'm missing that. Maybe plus or minus something equals 0. The a and the b here, they have to multiply together to give us 6. So 1 and 6, or 2 or 3. This is kind of standard factoring trial and error that you try to do. And let's see, the cross term, we want it to be negative. So I'm going to use a -3 and a +2. Right? And I multiply this out as a check. I get e to the x squared. That's the first term. I get, when I do the last, I get -6. That's correct. I get +2x and -3x, e to the x, and -3 e to the x. That comes out to be the negative e to the x that I want. Okay. So why do we factor? So it's easy to lose track of this when you're in the middle of something brand new and difficult, but the reason that we factor is because now we can set each factor equal to 0. The only way a product of two things is 0 is when one or the other of the factors is 0. So we're going to solve this pair of equations now. Okay, so try to solve this first one. E to the x equals -2. We're trying to isolate the x, so that seems natural to move the constant to the other side. And now we need the x. In order to get the x, it looks like if we take the natural log of both sides, we should be in business. Okay, so you can, maybe you're shouting at the screen right now already, having spotted my error, but I wanted to go ahead and play this out. All right, so going to your calculator, then you get x is equal to the natural log of -2, and here we get, this is cancellation, x is equal to natural log of 3. If you went to your calculator and plugged in natural log of -2, you'd get an error, and that would tell you that this is not really a solution. X equal natural log 3 is a solution, and it's the only solution, right? So it's okay if you go to your calculator and at this point see that natural log -2 is undefined and simply cross this one out. Again, I'm talking about you're doing written work on an exam or something. As long as you eventually cross this out, it's okay. But I do want to back up maybe all the way to this equation. As soon as you wrote down this equation, we're looking for an exponential to equal -2. Well, if you remember the graphs of exponentials, they're always above the x-axis. So maybe right at this point, to save yourself some time, if you remember that, you could cross out this solution or this non-solution before doing these extra 2 steps. All right, so this is So false. Oh geez, how do I denote this? Let me just say undefined. And this one here, oops, is only solution. Okay. Right, so that's a quadratic type, and this one has been handed to you in the most helpful way possible. The exponential you see, and then you see the exact same exponential literally squared. This is a more common type of homework problem, or I'll say an exam problem, is when the quadratic type is slightly obscured. It's not immediate in the original equation. And to recognize that this is quadratic type, you need to be able to apply this rule of exponents. You need to be able to say to yourself, oh, this e to the 2x rule of exponent says that's exactly the same thing as, well, e to the x and then, oh geez, squared. So you need to be able to make that transition onto the explicit form for quadratic type on your own. So, all right. Yeah, it's going to be kind of a long lesson today. Again, press pause, go work your homework for a little while, take a break if you need to. This last technique for solving exponentials, and then we'll get on to log equations, is a general technique that you can apply to lots of different types of equations. So the idea here, is wherever you see the exponential in your equation, do a substitution. And you get to pick whatever letter you like. A common letter for substitutions is u. So we're going to rewrite the equation with the letter u in place of 2 to the x. So let's do that. Equation is, well, it's 45 over 1 plus u equal 5. And now we're going to solve this equation for u. Okay, so this is no longer having anything to do with exponentials, but it does demand that you still have some algebra skills. We're going to clear the denominator. I guess we could cancel the 5. This would be 9 equals 1 plus u. And so it looks like the u is equal to 8. Now switch back. So when we switch back, we remember that the u was 2 to the x. So we have 2 to the x equals 8, and that 8 is 2 cubed. And so our answer here is x is equal to 3. You take log base 2 of both sides. Okay, so the idea of the substitution is that it made the symbolic work that we did on solving this equation a little bit easier. We didn't have to worry that our equation was carrying around an exponential. We just had to solve for the letter u. Right, right, so let's try one more here. So this is demanding a lot of us to try to solve this equation, but we're going to give it a go. What we're going to try to do is get a single base here instead of 2 different bases. We have a 4 and a 2. So our first step is going to be to try to get an equation where we have just a single base. So we can write this as 4 is 2 squared, and then 2 squared raised to the x is same as 2 to the 2x. Okay, so that's one step. Maybe I should have done that in 2 steps. And then the next step is we're going to split this exponent apart as 2 times 2 to the x. Okay, so this was supposed to be an example of substitution. I'm not sure it's really critical, but I'll go ahead and do it. We're going to say let u equal 2 to the 2x. Right. Then our equation becomes u plus 2u equals 12. becomes 3u equals 12, and u equals 4. And then we can return to the exponential form for the u there. Just substitute back in what it was. 4 is the same as 2 squared. And so finally we come down to 2 squared equals 2. And so our solution here is x equals 1. Yeah. I'm just checking here. I plug in 1, I get 4. Plug in 1 here, I get 2 cubed. And so that's 8, and that does pan out. Oh yes, so we're at 25 minutes already. Oh my goodness, this could... The good thing about the log equations is there are far fewer forms to worry about. Okay, so this time for a log equation, we mean an equation where the variable that we're trying to solve for is tucked inside a log function. And the general strategy here for all of these is to combine all of the logs together, probably on just one side of the equation, take exponentials, and then solve. I guess, and then, this is important, I shouldn't forget to say it, check the solutions. It's very common that you wind up getting extraneous or extra false solutions as you do this, so you always want to check your answers at the end. Okay, so we're going to solve this equation, combine all the logs using log laws. So this is something we practiced last time. This is the log, a sum of two logs, and so we can combine them as the log of the product. Oh, shoot. And now the suggestion here was to get all of the logs to one side. I would say that that's not critical, but just to try to be systematic about it, I'll go ahead and do that. So how am I going to get the log over there? I'm just going to subtract from both sides. Okay. All right, and then I'm going to combine into a single log by using the law for quotients. Okay. So we've done what it said, combine all the logs on one side using log laws, and now we're going to take exponentials. So our variable is buried inside the log. The way we're going to get to it is by taking 10 raised to both sides. On the left-hand side, the cancellation of 10 and log base 10 is going, well, they're going to cancel. On the right-hand side, we're going to get 10 to the 0, which we have to remember is equal to 1. The left-hand side simplifies. X squared and upstairs and downstairs, this is just x over 2. And then the last step here, we multiply it through and get x equals 2. Right. Check. So checking just means that we're going to plug in log of 4 equals log of 2 plus log of 2. Yes, and that's by the log law. Okay, so there's a warning on this. This is a temptation I've seen students succumb to quite often, and you have to resist. There's this temptation to take 10 raised to both sides right out of the gate. You see logs on this side, logs on this side, and your temptation is, okay, I'm going to exponentiate both sides. And that's correct. It's not wrong to do that, but this next step is incorrect. The left-hand side is valid. We get cancellation there. But the right-hand side is not valid. 10 to the sum of two logs is not the sum of these two things. So I've spelled it out right here. So the advice here is to try to make sure you combine your logs before you exponentiate. Okay. Right, so another log equation, our variable buried inside a log. So idea here, we only have one log this time, but what we need to try to do is isolate it. And to do that, we'll subtract the 3 over, and then we'll I should just give myself more room. I don't know why I don't. Divide through by 4. And now we'll take the exponential of both sides. What exponential? Well, e, because we have base e log. So on the left-hand side, we'll get cancellation. On the right-hand side, we'll get e cubed. So lastly, we'll subtract off the 1, and that'll be our answer. Check the answer. 4 times, I kind of feel bad because these are all working. I want to do as I say, and I said that you should check, but I know that these are going to work here. So natural log of e cubed, the 1's cancel on the inside there. So this is 4 times 3 plus 3, 12. Sure enough, it's 15. Okay. By the way, this is worth doing because this is an example where where one of the solutions is going to fail. So we combined the logs into a single log. They were already on one side, and then we exponentiate. So log base 10, we're going to take 10 on both sides. On the left-hand side, we'll get the cancellation, x plus 2, x minus 1. On the right-hand side, we'll get 10 to the first power, aka 10. Okay. This is a quadratic, but it's factored on the left, but you can't get fooled here. The right-hand side is not equal to 0, so we can't set these factors equal to 0. Instead, we need to FOIL out. Let's see, that's plus 2x minus x, so that's plus x and minus 2. Let's see, x squared plus x, so I need to subtract 10. So now I do have 0 on one side, and so now, fickle as I am, now I want to go back to factored form. A quick guess and check there brought it to me. I think I had that right. Okay, so it looks like x is equal to 3 or minus 4. Right, so now we check. So log of 5 plus log of 2, sure enough that's log of 10, and that's 1. We check the other solution though. We get log of minus 2 and full stop. This is undefined. No solution here. Okay. So what goes wrong with this technique? Well, when we apply the law of logs here, it's only valid for when the arguments, the things inside the logs, are positive. And because x is unknown at the beginning, we don't really know when to say the law is working and when it's not. I guess we could say, in order to do this, x plus 2 has to be bigger than 0, and x minus 1 has to be bigger than 0, and keep track of it as we go. But generally, it's just easier to check at the end to see if you have false solutions. Okay. Again, you go. I'll give you a countdown, and then click on the solution here. 3, 2, 1. Here's my solution. And I'll just leave you to read it. All right, last topic. We are at 34 minutes. I hope that this winds up being a very long section compared to most. Okay, so we now know how to solve exponential equations and log equations, hopefully. And here are some equations with exponentialism that you're already familiar with. So these exponential functions came up in compound and continuous interest. So let's review here. We invest $500. That's our principal. Our interest rate is 0.8, and this is compounded quarterly. That means 4 times per year. And our question here is how long until you have $1,000? So the T here is the question mark in this problem, the time. Right? So at the end of t years, hopefully you remember the formula for compounded interest. And we get 1/4 of the interest each year, and we have 4t compoundings each year. I'll go ahead and simplify that. This decimal is 1.02 raised to the 4t. And the question is, how long is it until this amount is $1,000? We'll write this in function notation. So the equation that we want to solve is a of t equals 1,000. Right, our formula for a of t is this. We've worked it out. So we want to solve this for 1,000. Oops, 1,000. T is in the exponent spot. That's what's making this an exponential equation. We're going to try to isolate it. Divide by 2. This will be 1.02 raised to the 4t is 2. So now this is completely by itself here. We got that constant a divided to the other side. And you might say, oh, I'll take log base 1.02 to get cancellation. But typically, again, we go to log base 10 or natural log when we do these problems. Okay, so on the left-hand side, we have to use the exponent law to bring the 4t out in front. On the right-hand side, we just have to be content with the constant looking the way it does, and then we divide through to solve for t. And I'll try to get my computer to give us a decimal for that. And that's something you should be practicing as well, so you can get your calculator computations working. So it's going to take us roughly 8 3/4 years, I guess 8 and 8 months for the $500 to make it up to $1,000. Okay, you invest $500 at 8% continuous. How long do you have? Okay, so let's see. Continuous interest earns a little bit faster. They were both at 8%, so we expect this to be slightly less than 8 3/4 years. But again, just a review of the players here. Our principal, 500, 8%. T is unknown. The compounding doesn't arise here because we're compounding continuously. Our formula, it's the PERT equation, 500 e to the 0.08t. And we are asked once again to solve 1,000 equal 500 e to the 0.08t. So again, dividing by 2, looks like I got my 1,000 on the different side this time. Oh well. It's a natural thing. And speaking of natural, because our exponential is the base e, the natural exponential, it makes sense to take the natural log of both sides here. And then finally we can solve for the t. Natural log 2 divided by 0.08 is our value for t. And to work that out as a decimal again, right, so 8.66 years. So as predicted, it was we doubled our money in a shorter amount of time because of the continuous interest. Okay. For these interest rate problems, we can also solve now, not just for time, but also for the interest rate. That's the other thing that is up in the exponent spot in the formula. So we invested 400 at the end of 3 years. So we're being told time is 3. Oh, the amount was 500. I don't have that in my table. Compounded monthly. And what was the interest rate? Okay, so the interest rate is unknown. Okay, so the general formula here, and this is 400. Again, it was monthly, so oh yeah, so the interest rate is unknown. It's a decimal, but it's unknown. And then this is 12t. So what we've been told is that at the end of 3 years, the amount is $500. So A of 3 is 500. Okay. 1, 2, 3, 4. That's enough, maybe. Okay. So A of 3. So here's the formula for A of t. The t is here, so we've got to plug in a 3 up here. And that's to be $500. Okay. Clean up a little bit. This is 36 in the numerator. I'm going to divide through by 400, and this will be 1.25. Okay. What I want to point out is that this is not an exponential. The thing that we're trying to solve for, the interest rate, is not in an exponent spot. It's just the numerator here. So what we're going to do next is simply take the 36th root of 1.25. Not a number I've looked at very often. And then finish up with the kind of standard things to get the r isolated now. 1 over 36 minus 1, and then lastly multiply through by 12. R equals 12 times this crazy number, the 36th root. Who knew? And we'll see if I can get a decimal spit out here. Boom. Okay, so that's in the ballpark of what a reasonable interest rate seems like, about 7.5%, so maybe that's the right answer. Okay, so that was a non-exponential, just to let you know that not all of the equations now are exponentials. However, with continuous interest rate, continuous interest, this solving for r is an exponential equation. All right, so 500, oh gosh, interest rate unknown. At the end of 120 years, the amount, I think I was trying to be funny here. I hope this doesn't wind up being a terrible problem to solve. So the formula for continuous interest is e to the rt up here. And what we're going to try to solve is $500,000 equals 500 E. The R is the unknown. It's the 120 years that we know. And we're trying to solve for R. Because that was the question. What is the interest rate? Solve this for R. Okay. So this is an exponential equation because what we're trying to solve for, the R, is in the exponent spot. All right, so let's see. Divide by 500 to isolate the exponential. This was 500,000, so this would be down to 1,000. Take natural log both sides. We're on the home stretch. Cancellation. Natural log of e to the 120 times r, and then finally divide through by 120. And I'll try to get that as a decimal as well. So for my computer, log is actually natural log, so I am getting the correct answer there. So it's going to take roughly 6%. All right, that was a long lesson today, 44 minutes. I hope you made it. We'll see you tomorrow.